Hello, welcome back. We have just been looking at resistors in series, and we saw that when we have resistors in series or series resistors, that in order to get the equivalent resistance, we just add the resistances together. Well, now we're going to look at what happens when we have resistors in parallel. So in order to do this, we're going to go to another light bulb puzzle. So light bulb puzzle number 3. The figure shows 3 identical light bulbs in a circuit. So we have light bulb A, light bulb B, and light bulb C. Initially, as we can see right here, this switch is not closed, which means that we cannot have a current going through light bulb C. So light bulb C will not be lit initially at all. And initially what we'll have is we'll just have the same situation that we had in light bulb puzzle number 1, where we have 2 light bulbs in series. And so we saw that the current into A must be equal to the current out of A, and therefore the current into B. And that must be equal to the current out as well. And since we saw that the current must all be equal, we saw that the brightness of light bulb A and light bulb B was equal. Now, what happens when we close the switch? So now that we have closed the switch, now when the switch is closed, there is now an alternate pathway for the current to get from bulb A back to the battery. So it doesn't have to go through light bulb B. We can also have a current that goes through light bulb C. And we see that, that the current that was going into A is now going to be split in 2. And it's going to go some into light bulb B and some into light bulb C. So light bulb C will now light up, and it wasn't lit before. However, the current that was just going through A and B only had one path, but now it has 2 paths to go through. So what we have done is we've allowed it to go through multiple pathways. We've opened an extra pathway for it to go. So what we have done is we've actually decreased the overall resistance of the circuit. And since we've decreased the overall resistance, and we remember Ohm's law tells us Ver, so in that case, if we decrease the resistance, and we know that the current is then equal to delta V over R. If we decrease the resistance, we increase the current. And so the current going into A is now greater, which means that A will in fact be brighter. All right, let's look at this in terms of a circuit diagram looking at resistors in parallel. So the figure below shows 2 resistors connected in parallel between points C and D. What that means is the left end of resistor 1 is attached to the left end of resistor 2, and the right end of resistor 1 is attached to the right end of resistor 2. And since they're attached, that means that the voltage at these ends, along with the voltage at point C, must all be the same. The voltage must be the same right there. The potential is the same. And the potential at the other side, on the right side of R1 and the right side of R2, must be the same as the potential at point D. So that means that the potential difference across resistor 1 must be equal to the potential difference across resistor 2, and that must be equal to the potential difference from point C to point D. Now, the other thing that we can see is that by Kirchhoff's junction law, the current going in, as we see, goes in, and there's a junction. And so it splits up into current I1 and current I2. That means that the current going in must be equal to I1 plus I2, the current coming out of this junction. So by Kirchhoff's junction law, the input current is the sum of the current through each resistor. So I equals I1 plus I2. Now the next thing that we know is we can use Ohm's law again, which tells us that we have Ver, and since we know that we have Ver, we can rewrite I1 as, because I is then equal to delta V over R. So we can rewrite I1 as delta V1 over R1. And we can rewrite I2 as delta V2 over R2. So now we see that we can have that I total is going to be equal to delta V1 over R1 plus delta V2 over R2. But wait, we already showed that delta V1 equals delta V2 equals delta VCD. So we can replace delta V1 and delta V2 by delta VCD. So here we have it written for delta VCD over R1 plus delta VCD over R2. Now I can factor out this delta VCD since it's a factor of both of these, for both of these terms. So if I factor that out, I see that I equals delta VCD times the sum of 1 over R1 plus 1 over R2. So now, suppose that we replace R1 and R2 with a single resistor with the same current I and the same potential difference, delta VCD. If we use Ohm's law gives the resistance between points C and D, and Ohm's law will tell us that, so we know that the resistance is going to be equal to delta V over I. And we saw that I was equal to delta VCD times 1 over R1 plus 1 over R2. So that tells us that RCD, if we take delta VCD over I, those delta VCDs cancel and we end up with 1 over R1 plus 1 over R2 to the negative 1. So we see that if we have two resistors in parallel, their equivalent resistance is going to be equal to 1 over the first resistor plus 1 over the second resistor, all raised to the minus 1, just 1 over that quantity. And that gives us an equivalent resistor for resistors in parallel. Resistors connected at both ends, that's what we call parallel resistors, or resistors that are in parallel. The left ends of all the resistors connected in parallel are held at the same potential V1, and the right ends are held at the same potential V2, as we just saw in that example where we just had two resistors. That means that the potential difference, delta V, for all of the resistors are the same across all resistors that are placed in parallel. So it doesn't matter if we have two resistors or if we have 100 resistors. If we have n resistors in parallel, their equivalent resistance is going to be 1 over R1 plus 1 over R2, all the way out to 1 over Rn, all to the minus 1. And the behavior of the circuit will be unchanged if the n Now, if we know that we can have the same potential difference across all resistors placed in parallel. If we want to measure that potential difference, we want to measure that voltage with a voltmeter, we're going to want to place it in parallel in our circuit. So here we have figure A showing a simple circuit with a resistor right here of 17 ohms and a real battery. That means that it has an internal resistance of little r and it has an EMF of 9 volts. So if we want to measure the potential difference across the resistor, we know that if we have something in parallel, it will have the same potential difference as well. So we can measure the potential difference across the resistor by connecting a voltmeter in parallel across the resistor. Now, in order for this to work, the resistance of the voltmeter must be very high. So if the resistance of the voltmeter is very high, then we're able to get a measure of the resistance of the voltage. And so in that case, the internal resistance right here, we wanted to figure out what that internal resistance is. That's going to be equal to the difference between the delta V that we measured over here and our EMF of our battery divided by the voltmeter reading times the resistance, times the resistance of our resistor. So we can find the internal resistance in our battery by finding the EMF minus the voltage that we're reading by our voltmeter divided by the voltage of the voltmeter or in the resistor times the resistance. And so in this case, that difference, this difference right here, will be 9 volts minus 8.5 volts. That'll give us 0.5 volts divided by our 8.5 volts times our 17 ohms. And that will give us an internal resistance of 1 ohm. All right. So that's how we can find the actual internal resistance of our battery by using a voltmeter in parallel. Now, another idea that we want to talk about is an idea of a circuit being grounded. So this idea of a circuit being grounded comes from the fact that the earth itself is a conductor. So if we connect one point of a circuit to the earth by an ideal wire, so it would be a wire with no resistance, we agree to call the potential of this point that of the earth, and the earth is going to be 0 volts. Now the wire connecting to the earth, the circuit to the earth is not part of a complete circuit. So there is no current in this wire. So a circuit connected to the earth in this way, we call it grounded, and the wire is called the ground wire. And if we look up here at this image of our 3-pronged plug here, so a circular prong of so the circular prong of the 3-prong plug is a connection to the ground. So this is our ground right here. Let's look at what this means in terms of a circuit diagram. So here we have a circuit diagram, and right here we have this thing called the ground symbol. So this means that right here, the circuit is grounded at this point. Let's try to figure out what this means. So here we have a circuit with a 10-volt battery. So here's our 10-volt battery. And we have 2 resistors in series. So if we have 2 resistors in series, we see that we have 8 ohms and 12 ohms. We know that our equivalent resistance for 2 resistors in series will just be 8 ohms plus 12 ohms equals 20 ohms. And that means if we wanted to find the current in this circuit, we use Ver, and we know that that means that our current is going to be equal to delta V over our equivalent, because the current through both of these resistors will be the same, through the whole circuit will be the same in this case. And so that will be 10 volts over 20 ohms. And that equals 1/2 volts over ohms is amps. And we see that's marked right here. So we have 0.5 amps. Now that means that if we have 0.5 amps and our first resistor is 8 ohms, then we do 0.5 amps times 8 ohms tells us that if we do our delta V equals IR, in that case, 0.5 times 8 gives us 4 volts. So our delta V across our first resistor is 4 volts. Now for our second resistor, we can say delta V equals IR, where I again is 0.5 and R is 12 ohms. So we see that delta V in this case will be 6 volts. Well, that's the potential difference. That's what we're getting when we do that. And we find the potential difference across our two resistors. And if we add these up, we see that we get, this will actually be a -4, be a drop of 4 volts here and a drop of 6 volts. So we end up with -10 volts total and a positive 10 volts on this side. So we will follow Kirchhoff's loop law. That works. All right, so let's see what it means now that we've added the ground symbol. So the symbol beneath the circuit over here, that's the ground symbol. And we know that the potential at the ground is 0 volts. So right here, V equals 0. I didn't say delta V, I said V equals 0, which means that right here, V equals 0. If that's true, and there's a change of 6 volts right here to get to 0, well, that means that at this point right here, the potential must be 6 volts. And if this was delta 4 to get to this point, then the potential, I'll put it up here, at this point, V equals 10 volts. And that makes sense. If it's 10 volts at the top of this, at the top of the battery and 0 volts at the bottom, that gives us also a delta V of 10 volts. So that works. So what we see is that by grounding the circuit, that allows us to have specific values for potential at each point in the circuit rather than just potential differences. So once we've grounded the circuit, now we know that this is V equals 0 volts. And that will let us know what the actual value for the potential is at different points in our circuit. All right, so we have gone over what happens when we have resistors in parallel and how we can find the equivalent resistance by doing 1 over each resistor, adding those up and raising those to the -1. And we've also looked at what happens when we have a grounded circuit and how that can help us to find the exact potential and not just the potential difference across at different points in our circuit.